Asia's largest clean tech media firm, is pleased to welcome everyone virtually to our exclusive webinar in collaboration with GIZ on integration of distributed PV in the Indian electricity distribution system. And now I would like to hand over the session to Mr. Kanchan Agarwal to take it further. Over to you, sir.
Good afternoon to everyone joining today from different parts of India, from different parts of the world, and welcome to this webinar series of 3 days, starting today till Friday. And this 3 webinar series we have designed specifically to share with you our key findings, our key results on some important studies that we have done with the support and the cooperation of the Ministry of New and Renewable Power, and as well as with the help of many of the DISCOMs in the country. And of course, our experts joining from India and from Germany. So today's topic is very interesting, as you have all seen the record-breaking lower prices coming up in the auctions. So we do hope that with this lower prices, maybe more and more PV is going to be added to the Indian grid system. And with this, the question remains that how much is sufficient, how much is possible, and what can be done. To answer those very specific questions, we have done a study to integrate distributed PV into the grid, and we are happy to share the results with us. And we have an expert panelist with us today who are going to discuss in detail with you. So, without wasting any further time, let us get started. And to begin, I will like to invite Mr. Yogi Gebler, Principal Advisor at Indo-German Energy Program, to share with us the opening remarks and as well as to introduce our key panelists for today. Over to you.
Yes, thank you, Kanchan. Warm good afternoon from GIZ, and on behalf of the German government. Welcome to a very exciting series of 3 days on a fascinating topic. Also brought to India from German experts in combination with Indian DISCOMs on how the integration of flexible, variable, fluctuating renewable energy such as solar is integrating into the Indian grids. And when we talk about grids, we always have to refer to the Government of India target, which is closing in almost monthly of 100 gigawatt by 2022. We believe, we as GIZ, now working with a portfolio of roughly 20 million euros on solar rooftop, we believe that the 60 gigawatt of ground-mount solar will come. As Kanchanji mentioned, we see record low tariffs on large megawatt scale ground-mount tenders. And there are several of them in the pipeline with organizations such as SECI. The struggle is still in the rooftop sector with almost 40 gigawatts to be accomplished, and we are not even close to show that pathway is going to be a successful road. On the end, we are seeing 7 gigawatts. We are seeing, as of today, we are seeing maybe 2 this year under the Corona pandemic to be added, despite the fact that India has the most attractive, which is called Phase 2 or Shrishti rooftop program the world has probably ever seen. I can use the terminology world, also I'm an American, so I'm allowed to exaggerate a little bit. And these 40 gigawatts are being facilitated now by DISCOMs, India's distribution licensees. We have 80 of them in the country, and we have 80 different situations, 80 different companies, either public, partially public, or partially private, are in a different shape, different mood, different mode to adapt to variable rooftop solar. And the question is why? Why is the perspective of 80 DISCOMs or 79 DISCOMs so different? from one to the other. So GIZ has undertaken this gigantic task to look at the distribution grid and to tackle, let's say, three main questions. Number one, are there any technical limitations to solar being added on the end of a distribution line, at the end of a feeder, near a distribution transformer? So at a household, is there a technical limitation to a grid, to an existing distribution grid? That is the question for today. Number two, the question for tomorrow: what are business models for distribution licenses to come or in existence? So we will address that also in a study which took almost 1 year now. And then day number 3 is the most exciting day for me because I have seen that study personally. It is looking into the role of replacing diesel generators with solar and with storage, electrical storage, with storage costs are coming down over the next decade. So what is to expect from this combination, solar and storage, and is that a viable business model for not only discoms but for individuals, homeowners, or even rescos, or even companies in the real estate sector saying we like to be on the clean end, we like to have clean buildings, and instead of having a capacity of diesel gensets which is barely or rarely utilized, and we can replace it with clean fuels, with clean solar and lithium-ion batteries in the near future. That is on Friday. So 3 days fully packed, and also in parallel with 2 large events happening in parallel in Delhi for the sector. One is the RE Invest, India's government's flagship show, this time virtual, on renewable energy per se, where Germany also has a pavilion. And also we have DAM, a distribution utility meet this week in Delhi. So I think we picked a good 3 days where people have the chance just to go back and forth among virtual events and get a lot of information presented. I like to turn now to our first presentation. I'm very happy to have with us Dr. Eckhard Tröster with Energy Nautics from Frankfurt, Germany. Energy Nautics is for us a very, very well-known firm because Energy Nautics helped GIZ almost 1.5 years ago to do the first grid integration conference in India. So this company comes with a strong expertise in that topic, how flexible, how variable solar and wind can replace a coal-fired or gas-fired or even nuclear-fired power plants. So I'm very happy that Mr. Tröster joined us today, accepted our invitation. I'm very happy that he is going to introduce a study which has been done a couple of years ago, but it's updated at least as we speak. This morning I had a long conversation with West Bengal, full of coal, full of PPAs, power purchase agreements for the next decade to come, unwilling to look into solar in a serious way. And for several reasons. One is a technical objection saying this solar feeding from behind will disturb our grid and damage our power quality. And these 2 technical, let's see, objections we're going to address with Dr. Eckhard Tröster now. Sir, I would turn to you now for sharing maybe your screen and for starting the presentation. After Dr. Tröster, we have Mr. Abhishek Ranjanji, head of the renewables at CS, a Delhi semi-public, semi-private discom with roughly 3.2 gigawatt of load capacity to be managed and a very high share in renewables, and his stand and what he thinks about solar penetrating his grid. And after that, I invite you to a vibrant panel discussion with several additional panelists, which I'm going to introduce later. Dr. Tröster, the floor is yours, but the screen is yours. Please go ahead. And Kanjan, I think you wanted to interrupt for a quick poll and how our audience looks like today. We have roughly 500 registered.
Before we invite Dr. Zoster to begin with his presentation, we would like to have a quick poll from you all to get to know you better, get to know the audience composition better, and what you think of the current state with the great integration of TV. So we have put on the first poll, and you can pick one of this based on the appropriate response, which matches you. So you have 30 seconds to vote for it. Okay, so let us check out the poll results. So we have a picture of the audience from the developer and the consultant side, and also on the manufacturer side among the financial services. So welcome to all in this webinar. Can we have the next poll, please? So today, as you know, we are going to discuss about safe level for solar penetration at the distributed transformer. So based on your own experience, what do you think is a safe limit of the solar PV penetration at the distribution transformer level? More 10 seconds to vote. You can vote for it based on your experience, based on what you think is possible. Crossed about 70% voting. I would now request to show the poll results. Say that safe level is 30% many of you also believe we can go even beyond 75%, which is good to know about that confidence. And some of you still believe that less than 30% would remain safe. Okay, so let us also get to the next question. So our next question is, what measures do you think is going to help in increasing the PV penetration level? Do you think, of course, since we're going to talk storage in the coming days in our webinar, so do you think that storage is going to be sufficient, or some other measures would be required? Do you think the storage can never be the solution, or do you think that currently need more data or more research to be done in this field? So I would then now close the poll in the next 2 seconds, and I would request to check out the results. So that's a big number of you, 72% of you have said this. So I'm sure we will discuss this in our today's discussion. Can we have the next point, please? So the strategies to be discussed, and also this is part of the study which will be shared with you. So what do you think is the best strategy? Is the best, or any of the option that you think, if any one option you think is the best, you can put for that. Yes. Open for a few more seconds, and now we can see the poll results. So a majority of you have said that not just a single one, but a combination of all these measures would be helpful. So thank you for your opinion. Let's go to the next poll question. So I think that the current regulatory framework and the current legal framework is sufficient to support very high penetration of PV. this is a very subjective question, so we just want to get your opinion whether you think it is sufficient or not. So yeah, I could see very quick answers from many of you. So let us now see the results of this. Also, we need much more better legal and delivery framework managed to support higher penetration of PV to the grid. I think we have one more question. Can we have the last question, please? So, thank you all for participating in today's poll, and then I request the toaster to start with this presentation. Okay, thank you, Sean. Thank you, Jörg, for the very kind introduction. Maybe I can share the screen. Maybe you can send a request. Otherwise, very good morning from Germany, and good afternoon to India. Jörg already introduced myself. My name is Eckhard Buss. I was Energy Nautics CEO. We are specialized on grid integration of renewable energies, and today I want to talk about our study we have performed a couple of years ago, as Jörg already mentioned, about PV grid integration of selected regions in New Delhi and Bhopal. So for the next 20 minutes, I want to talk about, give you a short introduction. I will give you some overview on the modeling and the scenarios we looked into. We then looked into different technology options, and then, of course, I want to show you some simulations results, and close my presentation with conclusions and recommendations. So, Jörg already mentioned by 2022, there's this large target of 100 gigawatts by 2022, and which 40 gigawatts should be rooftop PV. Not quite there, but I have heard that there are big steps are taken in India now, and for us, we have in order to prepare also for that, to get a better understanding of what's actually going on. If we add such a high share of PV, we have done for different distribution grids in Delhi and also in Bhopal investigations. We use the tool, the simulation tool, the Silent Power Factory for that, and very thankfully we're provided by data from distribution companies. And so let's have a look what kind of simulations or models we looked into. We had in overall 4, or actually 5 different distribution grids. One was in Delhi, it's more urban area. On the other hand, we had rural areas, 2 rural areas in Delhi, and then also in Bhopal, urban and rural feeder. The main differences, and that's quite important for solar, is if we look at the urban areas, and typically the lengths of the lines are quite low. The distribution transformer capacities are fairly high, but high peak loads to be observed compared to rural areas where there are overhead lines used, where there are long distances, typically an issue then also for voltages, and rather small distribution transformers, as we can see also over here. So we looked into these we developed models for these different grids, and then we developed a couple of scenarios, and I can't go into detail to all of the scenarios. The most important one is the question, where is actually the PV, where can we actually find the photovoltaic, where are the systems located? And we looked into like 2 different cases. One which is maybe more straightforward, say like normal distributed everywhere, every household has a small PV system, every house, compared to a more critical area or a situation scenario where basically the PV is then at the end of the feeder. And this typically then would give much more stress on the distribution system. So the loading of the lines will increase, the voltage issues will increase. So this is kind of more like worst case scenario to consider. Then the question is basically, you mentioned already, okay, how much can we actually integrate? Before we look at that, we need to understand the issues we are expecting when having renewables of photovoltaic in the system. First of all, we get with a very high share of PV, we get reversed flow, especially in situations when the load is low and the high PV or the sun is shining and we have a high PV in feed, and there can be a reverse flow. And this could actually then lead to overloading of feeders. It could lead to high voltages. Voltage limits might be violated. And therefore, it's important to look at specifically these issues in order to identify how much can we actually integrate into the system, what is the penetration level we can actually achieve. The conventional way to deal with this, if there's more and more PV coming in, would be then typically network reinforcement. That's what has been done in Germany mainly. So just put a larger transformer to add another cable, for example, or overhead line. Nevertheless, of course, there are also a couple of intelligent solutions which often maybe even come for free, and these also should then be looked at, and that's what we basically have done on the left-hand side. These are the different technology measures we have looked into. We had the base case, and we looked into on-load tuck changing with automatic voltage regulation at the power transformer. Wide area control, also a very important topic. I will touch on this a little later. Then typically there are shunt compensators involved. So how can they be involved to improve, for example, voltages? And there are the for free, more or less for free technologies using the PV inverter as services for controlling voltage, for example, with a fixed power factor or with here it's called QU characteristic. Some of you might know this as volt-var characteristic, which will then allow to control voltages on the distribution system. Further, we have the on-load tuck changing at the distribution transformers, quite common in some regions in Germany, however, quite expensive, we have to admit. And then also one option here is to cap the PV, so not to allow a certain power to go into the grid itself, which is also quite commonly used. I was a bit puzzled that you have chosen 0% for this option, because I think it's a pretty good option. We have some discussion on this maybe later on. Of course, the traditional solution is reinforcement, and then we have the topic of storage, look into storages, which you also have addressed to see that's quite a good option, basically. We have looked into two slightly different options. One is if you try to basically optimize yourself, so charging basically your storage right in the morning, and you will not be able to really release the grid. And on the other hand, if you do it a bit more intelligent, then it's called peak shaving, basically with storage, then you can actually don't lose any energy. That's nice, and at the same time you actually relieve the grid. And the last point here we look into is demand side management. So let's pick out some of these technology options to look a bit more into detail. First one, wide area control. What is it about? First of all, we need the power transformer. So we're operating here, this is shown at the medium voltage level, so assuming there's PV and load connected to this, or like the low voltage distribution transformers connected here. And what we do is basically we are taking measurements at the very end of these feeders in order to identify the voltage issue here. So for example, during the night, maybe also with more electric vehicles in the future, we have a very low load situation here. Therefore, we can then give this measurement data to the on-load tuck changer and allow for high voltage at this point. So therefore, we're not having any voltage issues. On the other hand, if there's a low load situation, a high PV in feed, then the voltage will be very high at this point. Therefore, we can step down here the voltage and therefore allow again for keeping the limits. This is a technology worldwide frequently used. Of course, it has some it has some issues or impacts because you need communication, you need measurements, and so on. So also some invest there. The second one I want to talk about is the inverter's capability to provide reactive power. As I mentioned, this is kind of for free, and it definitely helps if we have voltage issues in the system. There are various possibilities how to do this. Here you can see a cosine phi depending on the active power. I mentioned already volt var, a very typical technological solution commonly used. And this we also looked into, and we will have a comparison later on to understand what is actually impact, what are the solutions of these different measures, these solutions. And the other one, which I mentioned also, the capping of the installed panel capacity. So what is actually happening here is that although we have a certain rating of the PV module itself, we typically then say it's a DC rating or the inverter rating, AC, but the AC rating is already a fraction like 0.8, 0.7 of the panel rating. Nevertheless, what we can see here is that in many times in the year, basically these ratings are actually both the inverter rating as well as the PV module rating, the DC rating is actually not reached yet. So from this, we can, if we then reduce this further on the inverter itself, we can actually considerably reduce the loading on the grid itself. So as an example, if we go for 75% or 70% of the peak power, which basically means around about 50% of the panel capacity, we only lose around about 3% of energy, but we win more or less 20 to 30% in capacity on the grid itself. So from this perspective, it is indeed, in my opinion, a very interesting solution. Further, the topic of storage peak shaving, which is very similar to what to the capping. Nevertheless, of course, we do this with the storage. We are not losing the energy. And on the right-hand side, basically, you can see what happens is that the original part basically is shown here. So you have a very high peak during the midday, and this is then capped and reduced. So let's continue with the simulations and results. Just this out of the way. And so what we did is we looked at the different distribution systems, and then we started to increase the PV generation, starting with 20 or 15%, then 50%, 75, 100, and even 100% of always rated to the rating of the distribution transformer. How this translates in PV capacity is shown here, and therefore, so we have actually, for example, up to 54 megawatts in the rural area, or daily urban distribution system was smaller, therefore it was 8.1 megawatts. Okay, let's have a look how this was then continued. We looked at, or we identified the maximum PV in-feed profile or we combined the maximum PV in-feed profile with the minimum load, because then you will have the highest reverse flow on it. Yeah? And then we looked at the highest voltage we are observing. That's in the bottom. For example, here with 150%, it is 1.15, so 50% on top of the unit value, or then with the loading, for example, on the transformer itself, 150%. And these values we then look further into. So here is an example of the daily urban distribution grids. You can see the medium voltage grid. You see different distribution transformers over here. And on the left-hand side, you can see the voltage profile from the power transformer towards the different distribution systems. So here we are seeing a PV penetration of 20%. This is kind of more or less then compensating for the current load situation. That's why the voltage profile is very flat. There is no real overloading situation, low loading on the lines and transformers. Well, what happens if we go to 50%? And a reverse flow can be observed. You can see this especially in the low voltage systems, that the voltage is now increasing over here. We're getting some dark green zones starting to increase the loading on the distribution transformers. Continue at 75%. We already in the long line here, for example, which also leads to a fairly high voltage of 75%. And now we're at 100%, already almost touching the 10% limit. Over here, still everything is okay. The voltage is on the loading is below 100%, and obviously then with 150%, all the distribution transformers are overloaded. We can see it being red here, and also we have some voltage issues here with voltages up to 1.14%. So this we now have done for the different scenarios and also for all the different measures we can look into. And from this, this graph has been developed. You can see here. What does it show? On the x-axis, we can see the penetration rates, so 20%, 50%, 75%, 100%, 150%. So on the top is the loading. We said, okay, we don't want to have a loading above 100%. Okay, we know transformers typically can it's okay for them to have basically loading above 100% for a certain time. Nevertheless, of course, from a planning perspective, we should try to keep it below or at a limit of 100%. On the voltage side, we allowed for 6%. That's a recommendation on the medium voltage because we need some headroom for the low voltage side. And on the low voltage side, at a maximum plus minus 10% are allowed according to the international standards. So what you can see here is the different lines actually showing the maximum loading and the maximum voltage with the different measures which are actually seen. So please have a look at the black line. The black line is the base case. We have a pretty high loading in the very beginning. This is mainly due to the consumption itself. So consumption is also included here. But from a 75% share on PV penetration, then the PV actually takes over and the loading is increasing further and will then reach 100% and even further. So we can actually say at this point here, around about 90% of the distribution transformer, then we will have a overloading issue. What about the voltage? We are now here at Daily Urban looking into the low voltage system. So here the limit would be at 1 plus minus 10%. So we would find here. So we can then conclude for this. If we don't do anything, we operate our PV system at a power factor of 1, then we can integrate around about 90% of the distribution transformer without having loading issues. Obviously, this must be a line which has been overloaded, because otherwise, of course, we would only reach this limit at 100% or above. Now, all the other lines are showing us the different technologies we look into. So, for example, blue one looks a bit interesting. It's a higher loading compared to the black line, but it has a lower voltage here. And if we look into this, we can see, okay, this is a power factor, a fixed power factor for the PV system. So at all times, the PV system is actually then consuming reactive power, therefore reducing the voltage. So it helps a lot here on the voltage. We can see that. On the other hand, additional reactive power flows on the lines will actually increase the loading. So let's have a look at the different results. Now you have more or less understood these diagrams. So, for example, here we have the situation, the scenario that the PV is at the end of the feeder, so kind of worst case situation. And there already we can see that here at 75% PV penetration, we are already reaching the loading at the same time, but also reaching the voltage limit. So we can conclude from this, we should not have more than 55% in this specific feeder or in this specific distribution system. Otherwise, we will get an overloading. So here we can draw a line and say, okay, up to 75%, we are safe. And we have to remember this is actually a worst case situation. So how does it look in Bhopal, in the specific area we look into?
there, the loading was actually here at around about 120%, where we had an issue. We did not see any issues on the voltage level, and therefore we conclude we have actually gone up to 120%. So, but this is because the PV is equally distributed. We shouldn't not. This is not a worst case situation. So this is more like a normal situation, a normal load situation where you can actually then go further than 100% because you always have some load in the system which would actually consume directly the PV. So if you want to now to choose a solution, we go back into or we can have a look at the daily rural results. Here we have a medium voltage situation, so therefore the voltage issue is happening here around about 80% or 90%. And so we have to draw a limit here. And if we now want to find a solution which can actually help to increase the penetration level, what we can do is we can, for example, choose here the green line, which is the capping again. Yeah, so the green line is the capping, and there we can see if we do capping on the PV, we can actually increase or reduce the voltage, and therefore increase the limit to this value. This is also true for if we still have the green line for the loading. So we also have no loading issue, and we can conclude from this if we are including storage, in this case capping or storage, peak shaving is a very similar result. If we are including storage and peak shaving, then we can go actually up to 130% in terms of PV penetration without having any issues. And finally, for Bhopal rural, just an example where then we would end up with 100%. Also, it's a voltage issue in this case, so we can see that for rural areas, typically we have other voltage issues and loading issues. And again, we can say 100% is possible in this specific scenario, case, and model and situation. So let's have a look at the comparison of the different measures. I didn't put all here because I think that would be too crowded. So just looking at the most important ones. First of all, we can see that in the base case, we can go typically up to 90%. We have also seen that in the worst case situation, it's rather 75%. This is actually also our recommendation to go for 75%. If we add an on-load tap changer, we can see that in those areas where there's a voltage issue, like here in the rural area, that we can actually increase the penetration. We can even further increase it if we do wide area control, if you remember, so measuring at the very end, and therefore increasing from 90% to 105%. Where voltage issues are, we can also then improve the situation by using the reactive power of the PV systems, for example, here from 90 to 95%. However, in certain situations, then, or what I also showed you, if you have a fixed power factor, consuming reactive power, this will actually add more stress on the lines in terms of loading. So in this case, although we have a voltage issues, we are moving from a voltage issue to a loading issue, and therefore it's actually further reduced. What's nicer in this context is actually the volt bar characteristic or QV characteristic, as we call it here, where you can actually then also increase it and it does not impact on the loading itself. So the nice thing is about it, it's really then only activating reactive power if there is a voltage issues and not in the cases where actually voltage is good, but you still use a lot of reactive power. The two most interesting technologies, at least from like a penetration level perspective, are the capping of the PV. So we go up to 150% or 125% in this case, and the storage using peak shaving. Obviously, they have a large advantage for the increasing the penetration level. Nevertheless, they also have some disadvantages. Capping PV means up to like 3% losses in energy production. Storage means high invests and also some losses, of course, in storage itself. So these are not coming that quickly. But nevertheless, we can see that also in the base case, we have already the possibility to increase or to have a really high share integrated into the grids. So I want to close my presentation now with some conclusions and recommendations. So what we have seen is